Hello everyone, in this lecture I will discuss about the Riemann metric tensor. The Riemann metric tensor is represented as G mu nu, that is equal to this one, and this tensor is symmetric. And if we take all the diagonal entries is equal to 1 and off diagonal entries is equal to 0, then we get this one, and this is actually the metric tensor or Riemann metric tensor in Euclidean space. Okay. Actually, Riemannian geometry is the generalization of all the geometries. So Euclidean geometry is also included in that one, or we can obtain the Euclidean geometry from the Riemannian geometry. Okay. Now the line element can be written as this one. Now students, we know that in topological space we have a set x and a metric d associated with that set. In the similar manner, here we have a metric like metric space where Mn is a manifold and G is a metric, or you can say the Riemann metric tensor. Now you know that in Euclidean space, for example, we have 2 points. This is a point P, and say its coordinates are x1, y1 and z1, and here we have a point Q and its coordinates are x2, y2 and z2. Okay. Now if we want to find the distance between these 2 points, then the formula is very simple and straightforward, that is equal to pq vector, that is equal to x1 minus x2 square plus y1 minus y2 square and plus z1 minus z2 square. And also its line element can be written as ds square is equal to dx square plus dy square plus dz square. Okay. But students, the main difference between the Euclidean and Riemannian geometry is that the formula for finding distance between 2 points is different in the Riemannian geometry. For example, previously I have written down the line element as dx square is equal to g mu nu, dx mu and dx nu. Okay, where we are talking in 3D, so mu nu varies from 1, 2 and 3. So according to this, our line element will become equal to ds square is equal to d11. This is the most general metric tensor, and we can easily derive the Euclidean space when we take all the diagonal entries equal to 1 and all the other entries equal to 0, because obviously g11 will become equal to 1, g12 will become equal to 0 because this is an off diagonal entry in a metric tensor, and similarly all the other terms. Okay. Now student, this is actually the representation of first fundamental form, and also in a Riemannian metric tensor we have total of 9 components. Okay, and where 6 are independent components, because you know students, the metric tensor is symmetric. Symmetric means that this tensor is symmetric, and keep in mind that we can derive or we can obtain all the geometries from this metric tensor. This tensor is symmetric, that means g12 is equal to g21, g13 is equal to g31 and g32 is equal to g23. So total are actually 9 components, and due to these 3 symmetric components we get 6 independent components. Okay. Now students, this is all about this lecture where I have discussed about the Riemann metric tensor, and we have also obtained the Euclidean metric tensor from the Riemann metric tensor, and we have also discussed its little bit explanation. This is all about this lecture. Thank you so much.